This video covers the topic of absolute maximum shear stress and shear strain. You should have already covered the topic of in-plane maximum shear stresses and shear strains. Those are the maximum values that occur as you take an element experiencing either plane stress or plane strain, and you rotate it all the way around within that plane. And you look at the stress and strain components, and when you find the in-plane maximum is the maximum value that you get with that rotation. However, that's not the whole story. We can rotate that material around any of the coordinate axes, and shear stress components and shear strain components will occur. And we're really interested in the absolute largest of those because a material strength is dependent on its ability to resist shear. Specifically, its ductile response is dependent on its ability to resist shear stress. So we need to know the absolute largest value that it occurs on. And in this lecture, there are 3 learning objectives. The first is for you to be able to draw the Mohr circle that corresponds to the rotation about each of the 3 coordinate axes, not just rotation in plane, but 2 rotations out of plane. Second, use those Mohr circle to determine the absolute maximum values of shear stress and shear strain. And then third, be able to directly calculate the maximum value of shear stress and shear strain without using a Mohr circle. So the first concept I want to emphasize is that a material has 3 principal stresses. When we were talking about in-plane stresses, we only mentioned 2 principal stresses, sigma 1 and sigma 2. However, there should be some orientation in which none of the 6 sides of the material element experience shear stress. And we call that, all 3 of those normal stresses that occur on that material, we call them principal stresses when there are no shear stresses on any of the faces. In this class, we're going to limit our discussion to plane stress, which means that we will have sigma 1 and sigma 2, and the third principal stress will always be 0. There's 0 normal stress on the upper and lower surfaces when those surfaces have no shear stress. So therefore, 0 is a principal stress. In the broader scope of mechanics of materials, you could have a non-zero third principal stress, but that would be an advanced mechanics of materials topic and won't be covered in this class. So if we look at this plane stress state where we have 2 principal stresses, we can rotate it about each of the 3 coordinate directions. And so the first rotation is, for example, about the x-axis. So if we look at this material from the perspective of the x-axis and we look towards the material, what we're going to see are just normal stresses acting on the side, sigma 2, right? This sigma 2 is what we see here. And we're just looking at the YZ plane. So if we look at the YZ plane, here we have YZ plane, we only have 1 normal stress acting, and it's acting horizontally. So if we were to draw Mohr circle for this rotation about the x-axis, right? Because we could take this material and we could rotate it, and we could continue to rotate it and all the way around, and we could get the components, stress components acting on that material as we do that rotation about this x-axis coming out of the material. So when we do this, our Mohr circle will have a principal stress of sigma 2 and a principal stress of 0. Right? You would agree that this represents a principal stress state because there are no shear stresses acting on it. And in this principal stress state, we have normal stresses of sigma 2 and 0. Therefore, this becomes our Mohr circle. Now we can look at this from the perspective of the y-axis. And when we look at it from the y direction, So we come out here and look this way. Now our sigma 1 is the only in-plane normal stress if we're looking at xz as our plane. So if we're looking at the xz plane and we're rotating about the y-axis, so we're rotating this material about the y-axis, we can once again draw Mohr circle, and this time Mohr circle will have a principal stress of sigma 1, and we'll put that out here, and 0. Because it's sigma 1, we know that it's going to be larger than sigma 2, so I want to draw it graphically larger. All right, so this is our principal, or sorry, rather, this is our Mohr circle for rotating of this material about the y-axis. Passes through sigma 1 and it passes through 0, because those are the two normal stresses acting on this material when there are no shear stresses. And lastly, we can look at this material from the perspective of the z, looking down on the material, and that's when we end up with two normal stresses. So in this particular case, we have plane stress acting in the xy coordinate direction. Here's our x, here's our y, and that is sigma 1 and sigma 2. That means that as we rotate this material about the z-axis, we're going to get a Mohr circle. In its current state, there's no shear stresses, so we know sigma 1 and sigma 2 are our principal stresses, not to mention they're labeled as such. Sigma 1 and sigma 2 is how we identify principal stresses. Sigma 2 is always smaller than sigma 1, so it looks like that. They're both positive. That's why all these Mohr circles have been drawn on the positive side. And so there's our Mohr circle for this rotation. In plane, this is our in-plane stress state, because both of the normal stresses, both of the two non-zero principal stresses are in this plane. So I've shown you how we can draw the different Mohr circles for the three different rotations. And perhaps just to be real picky, I'm going to make this a little bit smaller. So if we want to do everything to scale, it would look more like that. All right. We can then superimpose these three, and what we get is a figure that looks like this. The first Mohr circle that I drew was this one here that connected 0 and sigma 2. The second one was this larger circle that connected sigma 1 and 0. And then the third one was this circle here that connected sigma 1 and sigma 2. So what this means is that whenever you start with your principal stress state, you have some value for sigma 1 and sigma 2, and then your third value in this class is always 0. You can make a figure that looks like the figure on the right, where one of your circles will always pass through sigma 1 and 0. That would be the biggest circle in this case. One of them will pass through sigma 2 and 0, and the other one will pass through sigma 1 and sigma 2. So essentially, it's like looking at the material in a two-dimensional format and recognizing that the normal stress components are going to vary somewhere between the two normal stresses that are shown on the material. So this one will have to vary as you rotate it. The normal stress will always have to vary between 0 and sigma 2. Here, the normal stress will always have to vary between sigma 1 and 0. And here, it'll vary somewhere between sigma 1 and sigma 2. And we know that that varying always takes the shape of a circle. So you end up with these three circles. Each one has its own maximum shear stress. The in-plane maximum shear stress is always going to be based on the circle that contains sigma 1 and sigma 2. Whereas the absolute maximum shear stress is based on the larger of the two circles. And sometimes these represent the same circle. Sometimes these are from the same circle, in which case the maximum in plane is the absolute maximum shear stress. But that's not always the case. So let's look at the three different scenarios. Depending on the relative magnitudes of sigma 1 and sigma 2, or rather the sign of sigma 1 and sigma 2, you get three different scenarios. You could have sigma 1 and sigma 2 both positive, or you could have sigma 1 and sigma 2 both negative, or sigma 1 could be positive while sigma 2 is negative. And in each case, we get a different looking Mohr circle. So let's draw the Mohr circle for each scenario. In the first scenario, where sigma 1 and sigma 2 are opposite signs, we have something that looks like this. We have circles that pass through 0 and each of our principal stresses. And then we have a larger circle that connects sigma 1 and sigma 2. In this case, sigma 1 and sigma 2 being connected represents our in-plane maximum shear stress. So this is in plane. And our maximum shear stress in this case can be computed as the radius of that circle, so sigma 1 minus sigma 2 divided by 2. So now if we look at the case of sigma 1 and sigma 2 both being greater than 0, that means, say, sigma 2 might be located here, sigma 1 might be located here. Now each of those will create a circle that passes through 0 when we do our out of plane rotation. But our in plane rotation is now contained inside. This is our in plane rotation. So this radius here is what we previously considered to be our maximum shear stress. But you'll see that the absolute maximum for this scenario is sigma 1 minus 0 over 2, or just sigma 1 over 2. And in this third scenario, sigma 1 and sigma 2 are both negative. So when we connect each of them, whoops, that's not drawn well. When we connect each of them to 0, we get two circles that are on the left-hand side of the tau axis. And the in-plane is once again a smaller circle. So this is the in-plane rotation. This is what we previously calculated as our in-plane maximum shear stress. But now our absolute maximum shear stress, you can see, is the radius of the circle that contains sigma 2. So that is calculated sigma 2 minus 0 over 2. So very important takeaway from this slide is that tau max in plane is always given by sigma 1 minus sigma 2 divided by 2. And in this scenario where sigma 1 and sigma 2 are of opposite signs, that will also be your absolute maximum shear stress. But in the other cases, it is simply this radial value here. But when it comes to your absolute maximum, tau max absolute, the equation appears to vary. But if we substitute sigma A, sigma B, and sigma C into these equations, we'll see it's actually the same formula. Now, sigma A is always the largest of your principal stresses. Sigma B is the middle, and sigma A, sigma B, and sigma C is the smallest. So we can identify these as sigma A, sigma B, and sigma C, sigma A, sigma B, and sigma C. And then if we substitute that down here into our equations, we see that in the first case, sigma 1 is sigma A, sigma 2 is sigma C. We get sigma A minus sigma C over 2. And in the second case, we see that sigma 1 is once again sigma A, but 0 is now sigma C. And in the third case, sigma 2 you know what? This is written incorrectly. I apologize. That would give you a negative value, wouldn't it? This should be 0 minus sigma 2. Because sigma 2 is a negative number, when you do the subtraction 0 minus sigma 2, you actually get a positive number. The way I had it, we were getting a negative radius. So my apologies. Okay, now this makes more sense. So now we plug in 0. Well, we know that that is sigma A in this case, and sigma 2 is sigma C. You can see that these are all really the same equation. That the absolute is sigma A minus sigma C over 2. And that's a fancy way of saying that you take the largest value of your principal stress, and you subtract the smallest value and divide by 2 to get the radius of that overall largest circle. So here you take the largest principal stress minus the smallest and divide by 2 to get that radius. Largest minus smallest, divide by 2 to get the radius. So if you know your 3 principal stresses, for example, you have a stress state that looks like this, 6, 6, and 3, you know that sigma 1 is a positive 6, sigma 2 is a positive 3, and sigma 3 is going to be 0. You can now align these from largest to smallest with sigma A, B, and C. So sigma A is the largest, 6, sigma B is the middle, 3, and sigma C then is 0. That's the smallest. So mathematically, if we want to calculate the principal stress, or sorry, not the principal stress, the absolute maximum shear stress, we would say that, no, I don't like that color. This one. We would say that tau max absolute equals sigma A minus sigma C over 2, which equals 6 minus 0 over 2, which equals 3 KSI. And if we draw the Mohr circle, you'll see we can get that same result by looking at Mohr's circle. So here, I'm going to first plot sigma 1, which is 6, and then I'm going to plot sigma 2, which is 3. I will connect each of those to the 0, and then I will draw my in plane, which connects sigma 1 and sigma 2. And I'll see that this outside circle, this one here, this gives me my largest radius. And because I know that the diameter of that circle is 6, right, you can see that it goes from 0 to 6, the radius must therefore be 3. So 3 KSI is my absolute maximum shear stress. So you can notice that in some situations, it might be faster to draw the Mohr circle, and I can see very quickly that the largest radius is 3, whereas I have to go through the math and get down to the same result. These same principles apply to shear strain. So for instance, if we have a positive strain in the x direction, here I have positive strain, and a negative strain in the y direction, I can make a Mohr circle for strain, and because there's no shear strain occurring on this, I know that those are principal strains. I can show here is the positive, here's the positive strain, strain 1, here's that negative strain, strain 2. Each of those is being connected to 0. And then the in-plane strain is represented by the circle that connects the two in-plane normal strains. And the third strain, which would be an elongation in this vertical direction or a contraction in the vertical direction, is 0, right? So strain 3 equals 0. That's why the two pass through 0. All right, from this, you can see that we have 3 radii. Each one corresponds to a different orientation of rotation, so rotation about different axes. And the largest of those, this one that I'm highlighting here in red, gives us our absolute maximum shear strain divided by 2. Here we have a strain state that is given. And if we want to draw a Mohr circle for this strain state, we would start by plotting the point strain of the x, gamma xy. So that's going to be the point 450 times 10 to the negative 6, comma, oh, I apologize. When this is strain, remember we need to divide by 2. So then this next point will be 275 over 2 times 10 to the negative 6, which is 137.5. So if we draw Mohr circle, and we draw that point, let's say 450 is say here, and positive 137 is say here, so we get this point. Next, we need to look for the center of this circle. So the center is going to be at the average strain, comma 0. The average strain here is 637.5, comma 0. Of course, those are both times 10 to the negative 6. So we will put that point approximately here. That then becomes our initial orientation of our element, and we can rotate that all the way around. Should look something like this. That is my in-plane rotation. It passes through my 2 in-plane principal strains. And then my out-of-plane is going to connect each of those principal strains to 0. Those should both pass through 0. Therefore, my absolute maximum strain is going to be this radius here. So I need to figure out the strain 1, and then from that I can figure out the absolute maximum shear strain. So to do this, we know that strain 1 equals our average strain plus r from our in-plane circle. So strain 1 is going to equal 637.5 plus the square root of 637.5 minus 450, quantity squared, plus 137.5 squared. Where that first part, this part here, is the difference between the two principal strains, strain 1 and strain 2. Oh, I'm sorry. No. That's the difference between the middle, sorry, the average and our strain X. So that is this distance here. And then this is our given gamma over 2. So that's this vertical distance here. So by doing the Pythagorean theorem, we're getting this purple radius there that I just highlighted. Okay, so from that, we are going to obtain that strain 1 is equal to 870 times 10 to the negative 6. And that means that our gamma absolute, our absolute max over 2 is equal, I'm running out of space here, where can we put this? Equal to 870 times 10 to the negative 6 divided by 2. Therefore, the absolute maximum value of gamma, because these 2's can both be removed from the equation because they're on opposite sides of the equation, this is simply equal to 870 times 10 to the negative 6. So that is the absolute maximum shear stress. We got that from determining, we knew that we only needed the strain 1 because we could see that that is what created this largest circle here. And that covers the topic of absolute maximum shear stress and absolute maximum shear strain.